Hello, this is Truth Socrates, and welcome to our video for today, which is about the 4 fundamental matrix spaces. So, what are we going to do in this video? We will learn what these 4 fundamental matrix spaces are. We will learn an operation on a matrix called the transpose operation, and we will find a basis for each of these 4 fundamental spaces. Why are we studying these 4 spaces? You will have to wait a couple of sections down the road, but spoiler alert, it is about solving systems of equations, just as you would have suspected. So here are our definitions. Let us take an n by n matrix A, and let us write it with the rows as row 1 to Rm, because there are m rows, and column 1 to column n, because there are n columns. The row space of A is simply the span of the rows of A. So they're the span of row 1, row 2, through row m. Each of these vectors has n entries because there are n columns. So therefore, the row space is a subspace of Rm. Similarly, the column space of A is the span of the columns of A. So we have the span of columns 1 through column n, and each column has m numbers. So therefore, the column space is a subspace of Rm. Our third definition is the null space of A, and it is made of all the solutions to the homogeneous system. Ax is the 0 vector in Rm. So the null space is all the vectors x in Rn, so that A times x is the 0 vector in Rm. Now, why should x be from Rn? It's because A has n columns. And remember, in order to form the matrix product A times x, you need to have x have the same number of entries as the number of columns of A. So that's why the null space is a subspace of Rn. Now, to define the 4th fundamental on matrices, it's very easy. There's no math involved. A transpose is the n by m matrix obtained from A by writing row 1 of A as column 1 of A transpose, and then writing row 2 of A as column 2 of A transpose, and so on. Now, when you write a row as a column, that also has the effect of turning a column into a row. Okay, so I like doing this. Okay, take your hand like this. If this is your matrix, you turn it over like this. Okay, so instead of going left to right, you go top to bottom in the same order. Okay, so here's column 1 at the tip of my fingers. That also becomes row 1 in the transpose. So rows become columns, and columns also turn into rows. Now, the 4th fundamental matrix space is the null space of this matrix, the null space of A transpose. So this time, they're all the vectors y from Rm, because the transpose now has n columns, such that A transpose multiplied by y gives you the 0 vector in Rn. And because y is from Rm, this is a subspace of Rm. So again, to define this matrix product, y must have the same number of entries as the number of columns of A transpose. And A transpose has m columns this time. Now, why aren't we studying the row spaces and the column spaces of the transpose? Well, we just said that column 1 turns into row 1. So therefore, the row space of the transpose is still just the column space of the original matrix. So there's no need to study the row space of the transpose or the column space of the transpose. We already have them from the original matrix. Now, how come these 4 fundamental matrix spaces are really subspaces? Well, let's review. There are 3 properties of a subspace. First, it has to be non-empty. the zero vector should always be in a subspace. It has to be closed under vector addition. If two vectors are from the subspace, the sum must also be in the subspace. And it must be closed under scalar multiplication. If you have a vector from the subspace and you multiply it by a scalar, the resulting product should still be in the subspace. We also saw in section 2.2, that the span of a non-empty set of vectors is always a subspace. So, since row space and column space are defined as spans of rows and columns, and the matrix has at least one row and at least one column, these are automatically subspaces. So really, we're just left with the two null spaces. And of course, the logic for the transpose null space is exactly the same as the logic for the null space of the original matrix. So, why is the null space non-empty? In particular, is the zero vector found in the null space of A? Well, the zero vector has to satisfy this definition. If you multiply A by the zero vector from Rn, you should get the zero vector from Rm. But that's fairly easy. If you multiply A by the zero vector from Rn, every column in A gets multiplied by 0. When you multiply a column by 0, you get the corresponding zero vector. Add up all the zero vectors, you still get the zero vector. So we get zero vector from AX, and so 0n satisfies the definition of the null space of A. And thus, 0n is a member of null space of A. So now let's talk about closure. Suppose you have two vectors, x1 and x2, from the null space of A, and k is any scalar. Let's think about closure under addition. So if these two vectors are from the null space, then they have to satisfy the equation found in the definition. ax1 has to be the zero vector 0m, and ax2 also has to be 0m. We have to show that their sum is also in the null space. Well, what happens to the sum when you multiply the sum to A? By the additivity property, A times quantity x1 plus x2 distributes as ax1 plus ax2. ax1 is 0m, ax2 is also 0m. Looks like we've seen this before. 0m plus 0m is still 0m. So that's closure under vector addition. And similarly, if you have a scalar product, k times x1, and you multiply that by a, you can use the homogeneity property, take out k, bring in a, and now you have ax1, which is the zero vector 0m, multiply it by k, you still get 0m. So therefore, our null space is also closed under scalar multiplication. And of course, the same logic applies to the null space of the transpose. All right, so whenever we're dealing with a subspace, the question is almost always, how do you find the basis for that subspace? So we want to find a basis for each of these four subspaces. And let's recall that a basis for a subspace W must span W, so the span of a basis B must be W, and B has to be linearly independent. So guess what? The key to the four subspaces is the RREF of A and of the transpose. So let's start with the row space. Elementary row operations do not change the row space of a matrix. In other words, if B is obtained from A using a single elementary row operation, then the row space of A is exactly the same as the row space of B. So consequently, if R is the REF of A, then the non-zero rows of R form a basis for row space of A. So let's think about this a little bit. How come a single row operation does not change the span of the rows? Let's start with the easiest one, swap. Okay? If you swap two rows, well, you don't really change the rows. Okay? So a linear combination of the original rows is exactly the same as a linear combination of the new rows, just in a different order. Now, what about if you scale? If you take one of the rows and multiply it, let's say, by 5, okay? How come the span of the new rows is exactly the same as the span of the old rows? So the key idea here is that all 3 row operations are reversible, okay? So if you have a linear combination that involves the original row, you just take the new row and you divide it by 5, okay? So if it was row 3 that got multiplied by 5, and you have a linear combination involving row 3, you just take the new row 3 divided by 5 and replace it with the old row 3. Okay, so the linear combinations are exactly the same. Now what about the third kind of row operation? That's always the trickiest one. Suppose you add, let's say, 4 times row 1 to row 2. So remember that in this case, it is only row 2 that changes. Row 1 does not change. So row 1 is the same in A as well as in B, the new matrix. So how do you get the original row 2 of A? So the key here is that the opposite of adding is subtracting. So given row 2 of B, to get the original row 2 of A, you subtract 3 times row 1 of A from row 2 of B. And remember that row 1 of A is exactly the same as row 1 of B. So therefore, a linear combination of the new row 2 involving the new row 2 found in B can still be expressed as a linear combination of the old row 2 from A. So therefore, the spans are exactly the same. Now, how come the non-zero rows form a basis? Okay, so since the span of the rows of the REF is the same as the span of the rows of the original matrix because the row spaces are the same, we have the spanning property. We're going to see in the example why we also have the linear independence property. It has to do with the positioning of the leading ones in the REF. Now, for the column space, we already know how to do this because we know the minimizing theorem. So it's said that if you look at the REF and you look at the columns containing the leading ones, then the columns of A corresponding to these columns form a basis for the column space. So I hope you noticed that these two spaces had something in common. For the row spaces, it's the number of non-zero rows, okay? But each non-zero row contains a leading one. And similarly, for the column space, you look for the leading ones. So therefore, if we believe these two theorems, then the basis for the row space and the basis for the column space have exactly the same number of vectors, and that is how many leading ones do you see in your REF. So the dimension of the row space and the column space are exactly the same, and in fact, it's the number of leading ones in your REF. So how about the null space? Well, we have been solving homogeneous systems of equations since section 1.6. So we follow the same recipe. You look for the REF, and then you solve for the leading variables in terms of the free variables. Now, what we're going to see is that once we do that, the number of vectors that we will need for our basis for the null space will be exactly equal to the number of free variables, not leading variables, but free variables. So if you have k free variables, then the dimension of the null space is going to be k. Of course, this also applies to the transpose. When you flip the matrix over, you look for its REF, and then you find its null space, just like we do for the original matrix. Okay, so I made a big matrix over here, and we're going to find a basis for each of the 4 fundamental matrix spaces. Let's start off by finding the transpose. So luckily, instead of having to write each column of A as the row of the transpose, we of course have a routine for that. Compute, matrices, and transpose. All right, so there is the transpose of our matrix. A is 5 by 7. The transpose is now 7 by 5. Okay, and let's look. Here is row 1, and here is column 1 of the transpose. So of course, if you read this left to right, those numbers will appear top to bottom in column 1. Also, here is, let's say, column 3. Okay, 0, 1, 1, minus 2, minus 2. Here is row 3 of the transpose, 0, 1, 1, minus 2, minus 2. Okay, so every row turns into a column, and every column turns into a row. Okay, we will deal with the transpose at the end. Right now, let's look for the REF of A. Compute, matrices, REF. Okay, so there is the REF. So check it out. Leading one, and then leading 1. So we have 3 leading ones, which means that we have 1, 2, 3, 4 free variables. Okay, so now we get to write a basis for each of the 4 subspaces. All right, so let's start with the easiest subspace, which is the row space. There's hardly any thinking involved. Just copy down the non-zero rows from the REF. So to save time, I'm just going to extract each row as a row matrix. I'm not going to put it in the usual vector notation, just to save time. Why should we have to put commas and braces and all that when it's very clear where each entry is located? So here is our basis for the row space. And its dimension, of course, is 3. So yeah, let's write that down. The dimension of the row space of A is equal to 3. So now for the column space, we will apply the minimizing theorem. We just look for the leading ones, and we copy down the columns in the original matrix corresponding to the leading ones. Okay, so we don't copy this column, that's just E1. The information is actually found in the original column 1. So let's extract, copy down here. Okay, I will scoot it up in a little bit. And then we have column 2, so that is over here. So let's put a comma here, and there's column 2. And then we have column 4, so that will be this column. So let's scoot that over here. When I scroll this though, we are going to lose this original matrix. So just to check, column 1, here's column 1, column 2, here's column 2, and column 4, this is column 4. So there you go, that's our basis for the column space. And again, the dimension of the column space of A is also 3. So next we're going to find a basis for the null space of A, and to do that we set up the homogeneous system from the REF, not the original matrix. So we're going to need some space. I'm going to scroll down. When I do, we're going to lose A, but that's okay. We only need the REF. We don't need the original matrix A. Scoot. There we go. Now we have space. All right, so the homogeneous system, imagine that you have zeros on the right side. So that 1 corresponds to x1, the 2 corresponds to x3, the 4 corresponds to x5, and the 5 corresponds to x6. Okay, there's a 0 here for x7, so x7 does not appear in the first equation. Set that equal to 0. Second equation, x2 plus 3x3 plus 5x5 minus 2x6 minus 9x7 has to be 0. Last equation, that is x4 plus 9x6. So x5 does not appear in the third equation. Plus 7x7 is equal to 0. All right, so now that we have our homogeneous system, we are going to create the solution vector. So I have prepped up x1 to x7. Let's make a copy of that here. And we are going to keep our free variables here. So that is x3, x5, x6, and x7. So we will erase x1 because we're going to solve for x1. And we will erase x2. We will solve for x2. x3 is free, so we keep it. We will erase x4. We will solve for it. x5, x6, and x7 are all free. Okay, so again, x3 is free, x5, 6, 7 are free. Solve for x1. It is negative 2x3 minus 4x5 minus 5x6. Solve for x2. Negative 3x3 minus 5x5 plus 2x6 plus 9x7. All right, x3 is free. Solve for x4, which is negative 9x6 minus 7x7. Okay, so that is our solution vector. So now to find a basis for the null space, we have to separate the solution vector into several individual vectors. How many? One for each free variable. So remember, the theorem said that the number of vectors that we will get for the basis, in other words, the dimension, is the number of free variables. So now we're about to see why that's true. I am going to make copies, 4 copies of this single vector. So we have this, plus another copy, plus copy, and plus copy. Okay, just to save some time. For the first vector, let's erase everything except the x3s. So there's a minus 2x3, erase this, there's an x3 there, erase this. Oh, nothing left, so that means there's a 0 there. That's not x3, make that 0, make that 0, make that 0. So erase everything which is not x3. Next, we will need x5. So erase everything which is not x5. If you're doing this by hand, of course, what you will write is what contains the x5. the term that contains x5 in each component. So x3 is not x5, return that 0. There's no x5 here either, so that's 0. x5, x6 turns into 0, x7 to 0. Okay, now we want x6 to be by itself. Minus 5x6, 2x6, 9x7 goes away, x3 turns into 0, minus 9x6, that stays, x7 goes away, x5 turns to 0, x6 you stay, x7 go away. All right, so finally, last vector, we want x7 to stay. There's no x7 in the first vector, first component. So that's 0. There's 7 there. Erase everything else. x3 turn into 0. Minus 9x6 go away. x5 go away. x6 go away. x7 by itself. Okay, so let me put this all in one line now that we have, there you go, now that we have every vector containing only one free variable. And will it fit? Let's try. Yeah, it fits. There you go. So that is the same vector and decomposed into 4 vectors. So finally, we will factor out the free variable from each of these 4 vectors. So take out the x3, and I hope you recall we did this in section 1.6. Now you know why. Take out the x5. Don't forget to put 1 where x5 is all by itself, because it's a free variable. x6, take it out, out, out. That's a 1. x7, out. And turn that into a 1. Okay, so the 4 vectors that we see over here will make up the basis for the null space. So we've done all the hard work, and these 4 vectors is our basis for the null space. Why? Well, this tells us that every solution to the homogeneous system, meaning every vector in the null space, is a linear combination of these 4 vectors. So that tells us these 4 vectors span our null space. What about the second property for a basis? Linear independence. So to do that, we have to form the test equation. When is a linear combination equal to the 0 vector? And we are in R7. When is it equal to 0, 7? Now, there's a very sneaky way to solve this system of equations. And that's because we have all of these beautiful zeros and 1s. We will actually start from the very last component, the 7th component. For x7, that's a 1. But look, everyone else is 0 for the 7th component. Ah, okay. So now that tells us if this linear combination is the 0 vector in R7, then the last component tells us that x7 has to be 0. Okay, so x7 must be 0. Anytime you have new information from the test equation, you can update your test equation. So now, let's copy that down here. And we can erase the last term because x7 is 0. That goes away. All right, but now, what can we say next? Well, let's look at the next component from the right, and that will be the 6th component. And what do we see? We have a 0 in the 6th component here, and a 0 in the 6th component here. So now, the 6th component now tells us that x6 has to be 0. And so on. I hope you see the pattern. Now you can erase the last term. You're down to 2 terms. What's next? This 1 in the 5th component tells us that x5 has to be 0. And finally, you have one vector left. When is the product of a vector and the scalar equal to the 0 vector? Either the scalar is 0 or the vector is the 0 vector. That's the zero factors theorem from chapter 1. I hope you remember that. So that's not the 0 vector, so therefore x3 has to be 0. All of the coefficients have to be 0, so that tells us that our 4 vectors are linearly independent. All right, so I've gone ahead and assembled, copied down these 4 vectors into our basis for the null space. And of course, we can say that the dimension of the null space of A is equal to 4. Okay, so the row space and the column space are both 3-dimensional, and the null space is 4-dimensional. Okay, but look, the original matrix had 7 columns. Okay, the row space and the column space are 3-dimensional. The null space is 4-dimensional. What's the relationship? 3 and 4 add up to 7. Okay, and that's because for the row space and the column space, you count the number of leading ones, 3 leading ones. For the null space, you count the number of free variables, which were x3, x5, x6, and x7. You have 4 free variables. That's the dimension of our null space. Okay, before we move on though, I want to show you something amazing. I call it sight reading the null space basis. We have the REF, and here is our answer, the basis for our null space that we got off from the REF. I'm going to show you a fast way to do this. Okay, so we had to write down the homogeneous equations, and then we have to solve for the leading variables in terms of free variables. I'm going to show you a way by which you can come up with these 4 vectors with hardly any effort. Okay, how? Check out the first vector. Okay, -2, -3, 1, 0, 0, 0. And this was the vector corresponding to x3. x3, which is a free variable. So, -2, -3. Those are the opposites of 2 and 3. But there's a 1 on the 3rd component because the free variable corresponds to x3. Let's check out this 4th vector. The free variable is x6. Look at the 6th column. We see 5 -2, 9. We see -5, +2, -9. So again, negatives. Okay, but you have to be a little bit careful because this 5, its leading one is in column 1. So that's why -5 is in the first component. -2, the leading one is the 2nd column. So you have +2. in the second component. 9, the leading one is in the fourth component. So that's -9 in the fourth component. However, okay, that looks a little risky, a little dangerous. I'm going to show you a surefire way not to make a mistake. So, first step, count how many free variables you have. So very easy. We have 1, 2, 3, 4 free variables. So we're going to create 4 vectors. Each of them is supposed to be from R7. So matrices, I have a 1 by 7 setup. There you go. We are going to make 4 of them. 1, 2, 3, 4. So this will be our final answer, our basis. We're actually going to write this down, but I'll show you how to write it down. Okay, so look for the free variables. Column 3. So put the 1 in the third component of the first vector. Next free variable, 5. So put a 1 in the fifth component. 6, 7. 6, 7. Okay. What else do we notice about these 4 vectors? To the right of the leading, no, that's not a leading one. I keep making that mistake. It's not a leading one. Think of it now as a trailing one. Okay, it's not the first number. It's the last number, which is not a 0. Everything to the right of that trailing one is a 0. So put zeros there. Next, same thing here. That trailing one is the last non-zero number in the second vector. So put zeros there. 1, 0. 1, well, there's nothing there. Okay, now what else do you notice? Below that 1, in the other vectors, everything else is 0. So it's kind of like when we did the REF, okay, where as soon as you have that 1, everything else in the column has to be 0. So that has to be 0. Underneath that 1, those should be zeros. So those are zeros. Under that 1, that's a 0. Okay, you will notice at this point that there are exactly the right number of blank components that we have corresponding to the number of components here which belong to those empty components. So again, for the first vector, look at column 3 because that free variable is x3. The 2 and the 3 go into that vector as the opposites. -2, -3. First vector is finished. Next free variable, column 4. Okay? But notice there's a 0 there. Okay? Don't be worried about that. 0 is still a number. Okay? But in this case, the 4 and the 5 belong in the second vector as -4, -5. But that empty space there, that's where the 0 goes. -0 is still 0. Sixth column. 5 minus 2, 9. They go in here. -5, +2, -9. Whoops, over here. There you go. Last vector. Now that's a 0, but it goes into the first column. -9 becomes +9, 7 becomes -7. 0, +9, -7. And of course, those 4 vectors are exactly the 4 vectors that we have over here. All right, so now we hack our final fundamental matrix space, the null space for the transpose of A. So let's find the REF. Okay. So that is the REF of our transpose. Okay, let's practice sight reading. Okay, so remember, step 1, identify the leading variables and the free variables. So leading 1, 2, and 4. Okay, free variables 3 and 5. Use sight reading to find a basis for the null space of A transpose. Okay, so we will need 2 vectors because we have 2 free variables. Each vector is from R5 because there are 5 columns. So let's put 2 vectors from R5. Here's one. Here's another. Okay, so free variables, column 3 and column 5. So you put the 1 at column 3, 1 at column 5. So to the right of the trailing ones, you will have zeros. Nothing to the right there. But below the trailing one, you should also have a 0. Okay, excellent. So now, go back to column 3. You have a 2 and a 1 there. So the 2 and the 1 go as -2 and -1. And the 1, 2, and 2 go into the second vector. So notice how you won't make the mistake of putting the 2 here because the 0 is already there, taking up space. Okay, so you will not make the mistake of putting the 2 in the third component. It goes in the fourth. So you have -1, -2, and -2. All right. So we have, of course, that the dimension of the null space of A transpose is equal to 2. All right, I owe you a little apology. In my excitement to get to the column space, I forgot to do something for you with regards to the row space. So for the row space, we said just all you have to do is copy the non-zero rows in your REF, okay? And we said in the theorem, now why is it that we get a linearly independent set, okay? And I said it has something to do with the leading ones, right? So let's test for independence, all right? We have the test equation. You want x1 times the first vector plus x2 times the second vector plus, I'm going to use x4 because 1 there's in the fourth component. x4 times that vector is the 0 vector in R7. Okay? Now this should sound familiar. We did it with the null space. Okay? So this time we go left to right as we do normally. Okay? Look at the first leading one, first component. Everything below that leading one is a 0. Okay? So now, first component tells us, can't spell, that x1 equals 0. Okay? So again, once you know that x1 is 0, you can update the test equation. Erase that. You are down to 2 vectors. When is this linear combination equal to the 0 vector? So this time, take a look at the second component. That's a 1, but below it you have a 0. So next, after updating test equation, x2 has to be 0. Okay, and of course, finally, x4 has to be 0. Okay, now as for the spanning property, we talked about the 3-row operations. We said, oh, when you swap, it's really the same rows. If you multiply by 3, then you get the original row just by dividing by 3. But we can actually explicitly see that each of these 5 rows can be obtained as a linear combination of these 3 final rows from the REF. Pick a card, any card. Okay, you can't answer me, so how about let's pick row 4. Okay, there's some interesting numbers in row 4. Okay, how can we express row 4 as a linear combination of these 3 vectors? Oh good, it still fits. Okay, so we're going to add them together, but we need scalar multiples. Ooh, it automatically adjusted to the next line. Okay, so let's talk about those leading ones and the zeros. Okay, first component, there's an 8 there, there's a 1 there, the others have zeros. So how much of the first vector do we need? Duh, we need 8 of them. Okay, so we get 8, 0, 16, 0, 32, 40, 0. That's still not that vector. But wait, there's more. We have a 1 in the second component here, 0 in the first vector, 0 in the third vector. So we need to get minus 6 in the second component, so that should be a minus 6. Okay, finally, we have one more vector. There's a 1 in the fourth component, 0 here, 0 here, minus 7 in the fourth component, so that should be a minus 7. Easy as pie. Let's check. Do we really get the same vector? Boom. Exactly the same. Okay, so let's finish off this video with a couple of definitions and a theorem relating these definitions. So we noticed that the number of leading ones controlled the dimension of the row space and column space. So that common dimension is called the rank of our matrix. So in our example, the rank of A is equal to 3. Okay, so we just worked with the row space. There were 3 non-zero rows in that matrix. Okay, now the dimension of the null space is called the nullity of A, and we said that we had 4 vectors for a basis for the null space. So the nullity of A is 4, and of course for the transpose, the nullity of A transpose, I believe there were two vectors in our basis. So the nullity of A transpose is 2. So we also noticed that 3 and 4, they add up to the number of columns. Okay, so we had 7 columns in A. The rank plus the nullity add up to 7. Now what about the transpose? Okay, we started out with a 5 by 7. When you transpose that, you get 7 by 5. So there are now 5 columns. We mentioned that the row space of the original matrix is just the column space of the transpose. So they have the same rank. A and the transpose are exactly the same. So we can write that's also the rank of A transpose. So now the transpose has 5 columns, and 3 plus 2, the nullity of A transpose, also add up 5. Not 7, but 5. So that is what's called the dimension theorem for matrices. Very easy to remember. For an m by n matrix A, the rank plus the nullity of A is n, the number of columns of A. Flip it over to the transpose, the rank of A transpose, which is the same as the rank of A, plus the nullity of A transpose gives you n, the number of rows of A which is the number of columns of the transpose of A. Okay, congratulations for making it this far. Thank you so much for watching this video. Again, you can find me on Facebook, and the 4th edition can be found on Facebook and of course at kendallhunt.com. Until the next time, enjoy the rest of your day.